Hey everyone, Mr. Hauk here. On Friday, we started the 8.2 area between curves notes, and we essentially got through example 4 here. All the examples that we did on Friday were for area between curves were all in terms of x. This video is going to cover how we calculate area between curves when the function is in terms of y instead. Okay, so just as a quick recap of what we did on Friday, we were looking at how to calculate area between curves. When we would set up our integral, we would use the top bounding function, f of x, minus the lower bounding function, g of x, okay, over whichever interval that we're interested in. Today, what's basically going to change, it's going to be the same setup, the same format, but instead of top bounding minus lower bounding with respect to x, it's going to be right bounding minus left bounding with respect to y, okay? And then the interval, instead of being x values, the interval is going to be the y values, going from bottom to top instead of from left to right. All right, that's going to be the big differences. So let's go ahead and see how this is going to set up. So the reasons we do this, well, sometimes you're going to be given equations that are already in terms of y, or you're going to be given functions that are, it's going to be easier to calculate the area if you change them to be in terms of y instead of rather in terms of x. So the idea behind this, imagine we are looking at a rectangular slice here. Let's say, and with respect to x, we had the vertical rectangular slices right here. Now we're going to be looking at horizontal rectangular slices. Where are we at? There we go. Okay, so imagine we did some kind of rectangular slice like that. And what we're doing here is we have this right bounding function, f of y, in terms of y, and this left bounding function, g of y. Again, both functions are in terms of y. So if I wanted to look at the width of this slice, let's look at the width of this thing. Well, the width would be represented as this point here from f of y minus this point here from g of y. So the width is being represented as f of y minus g of y, which we're really looking as the right bounding function minus the left bounding function, okay? And if I wanted to find the area of this slice, okay, I wanted to find, because remember, kind of the idea was in terms of x, we were finding the area of this slice, and we were summing up all those slices together. That's what taking a definite integral is taking an infinite area, an infinite sum of all those little rectangular slices. So if I calculate the area of this slice, well, the area of this slice would look like this. It would be that f of y minus g of y, that width, okay, times the height of the slice which is dy, that difference in the y values, okay? So the area of that slice is that width, dy. So the area of the region, if I want to calculate the area of this whole region, which is what we'd be trying to calculate, we'd be saying area of the region equals the integral from c to d. Notice I'm using c and d. This is the bottom of the region to the top of the region of f of y, right bounding function, minus g of y, left bounding function, dy. So the area of the region is going to be the sum of all these little rectangular slices if we made a bunch of rectangular slices. Okay? So this right here, similar to how we made a flashcard for area between two curves in terms of x, this is the area between two curves in terms of y. We want a flashcard for this. So effectively, all it is, we have our functions in terms of y. We're doing the right bounding function minus the left bounding function. The interval, we're using bottom to top y values, okay? Versus when we looked at x, it was left to right x values for the interval, top bounding minus bottom bounding, okay? This is right minus left from bottom to top for the y values, right? Let's see what an example looks like. So example 5, find the area of the region in the first quadrant bounded by the graphs of x equals y squared and x equals y plus 2 and y equals 0 by integrating with respect to y. So this is the same example that we did on Friday in example 4, okay? Same example here. Notice, however, that now we have our functions defined in terms of y. X equals y squared, x equals y plus 2. So this x equals y squared, or rather look at this y equals square root of x. This is the picture from example 4. This y equals square root of x, this is actually the x equals y squared. And this y equals x minus 2, that is the x equals y plus 2. So we have both of these functions in terms of y now, okay? And we can see that the right bounding function is the x equals y plus 2, and the left bounding function is the x equals y squared. And we are going from the y values of 0 to 2. 0 to 2. So if I wanted to set up the integral is going to be, to calculate this area, the integral from 0 to 2, right minus left, well, the right bounding function is coming from y plus 2, minus the left bounding function, which is y squared, dy. Okay? And look at why this is advantageous to us, or for us rather. Like if we look at example 4 we talked about on Friday, we had to split this up into two different regions. We had to split this up into region A and region B, because when we do this with respect to x in terms of x, for region A, the top bounding function was coming from y equals square root of x. The bottom bounding function for region A was the x-axis. But then when you look at region B, top bounding function, still y equals square root of x, bottom bounding function for this area, no longer the x-axis, now is y equals x minus 2. So we had to split it up into these two different definite integrals because the top and bottom bounding functions weren't the same consistently throughout the problem, throughout the area that we were trying to calculate the area, or the shape we were trying to calculate the area of. But for this thing, notice that this x equals y plus 2 is always going to be the right bounding function, and the left bounded function is always using this x equals y squared. So this allows us to calculate the same area that we did on Friday in one step without having to split up the integral. All right. So let's go ahead and calculate this integral. I'm just going to rewrite it. Negative y squared plus y squared plus y plus 2 dy. Let's take our antiderivative. This is going to be negative y cubed over 3 plus y squared over 2 plus 2y evaluated from 0 to 2. All right, let's evaluate at the upper bound first. 2 cubed is 8, so that's going to be negative 8 cubed. Sorry, negative 8 over 3. Plus, then 2 squared is 4. 4 over 2 is 2. Plus 2 times 2, that's going to be 4. Minus, and then here, evaluate at the lower bound. If we plug in 0 for all the y values, we're just going to get one big 0. So we have negative 8 thirds plus 6, which is negative 8 thirds plus 18 thirds, which is 10 thirds. All right, I can't remember if we actually calculated the area of example 4. No, we didn't, because here it said write an integral expression. If you had calculated this, you would have got 10 thirds as well. Okay. So another example, example 6. This one is calculator active, so have your calculator next to you when we're doing this one. Find the area of the region enclosed by the graphs of y equals x cubed and x equals y squared minus 2. Okay, so here's y equals in red. This red function here is obviously y equals x cubed. We should know what that graph looks like. And then the one in blue is going to be the x equals y squared minus 2. Now, integrating with respect to y is a good choice in this one. So we're trying to find the area of the region enclosed here. That's going to be this region right here between these two curves. Okay, that's the area we're trying to calculate, the region we're trying to calculate the area of. And integrating with respect to y is going to be the idea here, because we have this y equals x cubed that is always serving as the right bound for that region, always. And x equals y squared minus 2 is always serving as the left bound for this region. Now, one thing we got to pay attention to, though, we can see that our left bounding function is already in terms of y squared minus 2. Our right bounding function right here is actually in terms of x. So we need to rewrite this by taking the cubed root of each side as x equals the cubed root of y. No, 3 cubed root of y. There we go. Okay, x equals the cubed root of y. But the thing is, remember, we need, when we're setting up our integrals, let's think about our integral here. Setting up our integral, we have to go bottom to top. The bottom here, the y value at the bottom, because we're going to do this with respect to y, the y value at the bottom is pretty clearly a -1 based off of our picture. Okay, so that's going to be a y value of -1. In fact, the point itself is -1, -1. We can see the point pretty clearly. But this point up here, we're going to need to use our calculator for. Okay, so let's find that point of intersection. So let's do the point of intersection, points of intersection. Okay, obviously to find the points of intersection, well, let's take these functions and let's represent them in terms of x, okay? Because when we're going to graph them, when you plug them into the graphing calculator, the TI-84, you're putting them into y1 and y2. You need to put them in terms of x. So we already have one function in terms of x, which is y equals x cubed. We're going to set it equal to the other function. Well, x equals y squared minus 2. Let's add 2 to both sides. Y squared equals x plus 2. And let's take the square root of both sides. Y equals square root x plus 2. Okay. Right there. All right, so, and sorry for the little time lapse there. I don't have my TI-84 on me, it's at the school, so I'm actually gonna have to use Desmos. Pulling up Desmos real quick. All right, so x cubed into y at 1, square root of x plus 2, into the other. And when you're looking at your graph, so let's do this here. Let's pull up Desmos. All right, so we have, again, y equals x cubed going into 1 equals, nope, cooperate here, Desmos, x not squared, x cubed, and then y equals square root x plus 2. Okay, notice it's not creating the full picture. I want to talk about that real quick. Over here, to get this square root off, when we took the square root of both sides, technically there's a plus minus right here. Plus or minus square root of x plus 2. So in Desmos here, if you put them both in, y equals positive square root of x plus 2, and it's same thing in your TI-84, and y equals negative square root of x plus 2. That's going to create the full picture. Now you can see the actual full graph here. In your TI-84, you would hit like second, calculate, and intersect, but here on Desmos, since again I don't have the TI-84 in front of me, I'm looking right there at that point of intersection. That's going to be that top bound, that top y value that we're going to use for our integral. So we can see it's the point 1.215, comma 1.793. So this is the point 1.215, 1.793. Okay. So that's going to be our points of intersection. We have points of intersection when x is equal, or I'll just list the points, negative 1, 1, and 1.215, 1.793. Okay, so setting up our integral to calculate this area, again, we're going to work in terms of y. So in terms of y, we're going bottom to top, y value from negative 1 up to y value of 1.793. All right, negative 1 up to 1.793 of right bounding function, which was cubed root of y, minus left bounding function, which is being created by y squared minus 2. Make sure we're putting that y squared minus 2 in parentheses. dy. Okay? Now, when you put this in the calculator, something you got to be careful with, or not be careful with, but just understand. Yes, we are calculating this with respect to y. You know, we're using our y's, we set it up with respect to y. When you put it in the calculator and you do math 9, the finite integral, again, you're going to be using the variable x in the calculator. Remember, variable is just a placeholder. Okay, we set it up with respect to y, but when you put it in the calculator, use math 9, you're going to be using x in the calculator, but with the values that we got by setting it up with respect to y. Okay, but throw that into math 9, do this, make sure that you're doing this and getting the same answer that I got. I got 4.215, rounding to 3 decimal places. Okay. All right, our final example from Friday's notes, and this is the kind of example that I've seen show up on the AP exam and the free response from time to time. So it says, example 7, let R be the region enclosed by the graph of f of x equals x to the fourth minus 2.3x cubed plus 4, and the horizontal line y equals 4 as shown in the figure below. So this is not calculator active. Obviously, horizontal line y equals 4 is going to be this one. We have the function f of x is going to be from this curve right here. Okay. The vertical line x equals k divides region R into 2 subregions of equal areas. Write, but do not solve, an equation involving integral expressions whose solution would give the value of k. All right. So write but do not solve an integral expression, or an integral equation rather, involving integral expressions whose solution would give the value of k. So the idea here is that there is some vertical line x equals k. There's some x value of k that when we make a vertical line going through it, it's going to divide this region R into two subregions of equal area. So we don't know where this region, we don't know where this x value of k is, but just for a visual, let's imagine it was like right here. Okay. Let's imagine we had some x value of k, and that these two subregions here and here, imagine they had equal area wherever that x value of k is. Okay. So we want to set up an integral that would help us find what this value of k is. So what I'm thinking is we can say something along the lines of, and notice by the way that I'm going to work in terms of x. I have a top bounding function for this region, which is always going to be y equals 4, and a bottom bounding part of the region, which is always being generated from the function f of x. So top bounding and bottom bounding, I think we should definitely work in terms of x, not in terms of y here. So here's what I'm thinking. First off, let's go ahead and get our points of intersection. Here and here. Now, one of the points of intersection is pretty clear, from the picture at least. 0, 4. Okay. The other one we're going to have to algebraically find. So points of intersection, let's go ahead and find them. All right, so we're taking our two functions, we're setting them equal to each other to find the points of intersection. So we're going to set x to the fourth minus 2.3x cubed plus 4 equal, and the other function is just 4, y equals 4. Okay, well, when we subtract 4 from both sides, this is going to give us x to the fourth minus 2.3x cubed equals 0. Let's factor out an x cubed. We get x minus 2.3 equals 0. This one, x cubed equals 0. This factor, x minus 2.3 equals 0. Here you'll get x equals 0. Again, that's the one that we could visually already see, but there's algebraic proof as well. And then the other one's going to give us x equals 2.3. So this has an x value of 2.3, y value of 4. Okay, so 2.3 comma 4. So our integral setup, well, let's think about how we could actually do this. There's a few ways that we could set this up. I'm actually going to show you 3 different ways, 3 different integral setups that would work, that would gain credit here. So the first one that I can see, again, remember, this x value of k is splitting this region R into 2 equal areas. So if I go from the x value of 0 to the x value of k, that should equal the same, an integral that would go from k to 2.3. So I would write, here's one possibility, I would write the integral from 0 to k of the function, well, remember it's top bounding minus bottom bounding, 4 minus this whole thing right here, 4 minus f of x dx. So going from 0 to k should equal the integral from k to 2.3 of the same setup. Okay, and that would meet the criteria. This would get us credit because we wrote an equation, equation involving integral expressions whose solution would give us the value of k. So if we actually calculated this and we found the antiderivative and did our fundamental theorem of calculus and evaluated at the upper bound minus the lower bound, we'd get an expression on both sides that involved the variable k, which we could then solve for the value of k. Now we don't have to solve for it. It says write but do not solve. But this is an equation involving integral expressions that could help us solve for it. Or, here's another solution that would work. We could also say that the integral from 0 to k of top bounding function 4 minus lower bounding function f of x, we could say that same integral is equal to 1/2 of the entire integral from 0 to 2.3 of 4 minus f of x dx. Okay, that's another possibility that we have. Or even a third way, this would also gain credit. Again, we could say, well, what if instead of doing 0 to k, we did k to 2.3? Okay. Oh, go away. K to 2.3, 4 minus f of x dx. That could also be half of that entire area. Okay, so all three of these involve an equation involving integral expressions that could help us find the value of k. All right. Now, for homework, I want to talk about homework real quick. What you should have picked up is, it should say 8.3 Plato Lab. On eClass, under the content section where you normally find keys to notes and practices and things like that, there's a video made by the former BC teacher, Ms. Jasani. It's a video going over that Plato Lab. She made it during the digital year, the hybrid year, where half were online, half were at home, or online, half were in the building. So she made that video for students that were at home that couldn't do the Plato Lab in class. So it's a video where she actually goes over the Plato Lab. Your homework is to watch that video. It's about 20 minutes long, and to fill out your paper along with her as you go. This is a good precursor to what we're going to do in Tuesday's notes, which is going to be calculating areas based off of known cross sections. Okay? Have a